Assalamu alaikum wa rahmatullahi wa barakatuh. Hello my student. We will continue our topics in the same chapter, chapter 8, DC motors and generators, part 3. Introduction. DC motors are DC machines used as motors, and DC generators are DC machines used as generators. The same physical machine can operate as either a motor or generator. It is simply a question of the direction of the power flow through it. This part of lectures will illustrate the working principles of DC motors, and then we'll examine the different types of DC motors that can be made and explain the advantages and disadvantages for each. Okay guys, so we're gonna start now with the motors. Already we finished the types of the DC generators. Now we will start with the types of DC motors. As stated earlier this semester, mechanical energy is changed into electrical energy by movement of conductor through a magnetic field. The converse of this is also true. If electrical energy is supplied to a conductor lying normal to magnetic field, resulting in current flow in the conductor, a mechanical force, and thus mechanical energy will be produced. DC motors are often compared by their speed regulations. The speed regulations of motor is defined by what? SR, speed regulation, equal speed at no load minus speed at full load over what? Speed at full load. Okay, so omega motor speed expressed in rad per second, and n would be what? Express the speed expressed in revolution per minute. Okay, let's move to the next slide. It is a rough measure of the shape of the motor's torque speed characteristics. A positive speed regulation means that the motor's speed drops with increasing load, and a negative speed regulation means a motor speed increases with the increasing load. The magnitude of the speed regulation tells approximately how steep the slope of the torque speed curve is. DC motors are driven from a DC power supply. Okay, we need DC power supply for the DC motors, unless otherwise specified. The input voltage to a DC motor is assumed to be what? Constant, because the assumption simplifies the analysis of motors and conversion between different types of the motor. So again, here we have 5 types of DC motors. Okay, the first one will be what? The separately excited DC motor. The second will be the shunt DC motor. The third, the predominant magnet DC motors. The fourth, series DC motors. And 5 will be the compound DC motor. Okay, like what? Like the types of here of the DC generators. Okay, so let's start with the first section here, 8-2, the equivalent circuit of a DC motor. The equivalent circuit of a DC motor is shown in figure 1. There are a few variation and simplification of this basic equivalent circuit. The brush drop voltage is often only a very teeny fraction of the generated voltage in the machine. Therefore, in cases where it is not too critical, the brush drop voltage may be what? Left out. Okay, left out. Also, the internal resistance of the field coils is sometimes lumped together with the variable resistors, and the total is called what? RF. Another important notes are that comparing the equivalent circuit of the DC motors with the generator, we can see that the armature current follows from the output from the outer power supply VT into the armature coil. So because we are supplying now, okay, we are supplying now the armature with the current from the voltage terminal, and that because in motor case we change the electrical power to mechanical one as mentioned before. Moreover, the load term of in motors means mechanical loads, not resistors load as we did with the generators. Okay, so the internal generated voltage in the machine EA is given by what equation? EA equal K flux omega. Okay, this is the equation, and we can notice that the identical to that for generator. It is the same for generator, this equation. And the induced torque developed by the machine is given by what? Torque induced equal K flux current IA. Okay, this is these two equations, the Kirchhoff voltage law and the torque equations are all the tools necessary to analyze the behavior and performance of the DC motor. By the way, this is the figure 1, the equivalent circuit of the DC motor. Okay, let's zoom in. Okay, guys, as you can see here, we have this is the armature with the brushes EA. Okay, this is the V brush, this is the throb V brush, and this is the RA with a low value of resistance. This is IA. Can you see that? This is the VT terminals. This is the power supply here. We can supply power supply. Can you see the direction of the current now? Goes to what? To the armature. From power supply to what? To armature. Before for generator it was what? From the armature goes to what? To the VT. Okay. Now also this is the what here RF with the IF I field with the resistance of the field. Okay, now section 8-4. Section 8-4, separately excited and shunt motors. The equivalent circuit of a separately excited DC motor is shown in figure 2A, and that for the shunt motor in figure 2B. Separately excited DC motor is a motor whose field circuit is supplied from a separate constant voltage power supply. While a shunt DC motor is a motor whose field circuit gets what? Whose field circuit gets its power directly across the armature terminals of the motor. When the supply voltage to a motor is assumed constant, there is no practical difference in behavior between these two machines. This is why we put it, the two types here in one section. Okay, there will be no difference. Okay, because the supply voltage will be what as assumed is constant. The Kirchhoff's voltage law for the armature circuit of these motors is what? VT equal what? EA plus IA multiply RA. Do you remember for DC generators it was VT equal what? EA minus IA multiply what? RA. This is for what, guys? For generator, DC generators. But now this is the new equation will be what here for what? DC motor. It will be what? Plus. It will be, guys, here a plus. Okay, let's move to the next slide. This is the equivalent circuits, okay, for shunt and for separately. So the first one here, A, will be what, guys? This is for here for shunt. As you can see, this is this field will be what, across the armature with what, with RA in parallel. Across mean parallel. We have IF equal VT over RF, and what VT will be EA plus IA RA. And about the current here, as you can see, the current will be IL equal IA plus what, plus IF, because the current here IL goes to the armature now. The next figure will be what, B, for what, equivalent circuit separately excited DC motor. Okay, we have VT, the same equation here, as you can see, VT EA plus IARA, and now here only we will have what, IL equal what, IA. For IF will be what here, VT over what, VT over RF. You have to memorize these equations when you solve the problems in shunt and separately excited DC motors. Okay, let's move to the terminal characteristics of what, of a shunt DC motor. A terminal characteristics of a motor is what, a plot of the machine's output quantities versus what each other. For a motor, the output quantities are shaft, torque, and speed. Okay, guys, shaft, torque, and speed. How does a shunt DC motor respond to a load? Suppose that the load in the shaft of a shunt motor is increased. What will happen here? Then the load torque will exceed the induced torque in the machine, and the motor will slow down. When the motor slows down, the internal generated voltage drops, okay, EA, decrease, so the armature current in the motor, what here, IA, will increase. As the armature current increase, the induced torque in the motor what, increases. Torque induced increases. And finally, the induced torque will what, guys, will equal the load torque at the lower mechanical speed of rotation. The output characteristics of a shunt DC motor can be derived from the induced voltage and the torque equations of the motor and Kirchhoff voltage law as follow here. Okay, omega equal what, VT over K flux, K multiply flux, minus what, RA over K flux square multiply torque induced. Okay. Now, this equation is just a straight line with a negative what, slope. The resulting torque speed characteristics of a shunt DC motor is shown in figure what, in figure 3. Okay, figure 3 here. A. Another effect internal to the motor that can also affect the shape of the torque speed curve is what, armature reaction. Okay, armature will affect the slope. If a motor has an armature reaction, then as its load increases, the flux weakening effect reduce what, its flux, as the speed equation shows. The effect of a reduction in flux is to increase the motor speed at any given load over the speed it would run at without armature reaction. So torque speed characteristics of the shunt separately excited DC motor with the armature is shown figure 3b. Okay, this is the terminal characteristics for both here. Okay, As you can see, this is A. This is with compensating windings. This is the ideal case. Okay, this is the ideal case. This is for A. This is for separately excited DC motors, and this is the normal case. Okay, normal case. There will be dropping in the speed as the load increases. Okay, B, this is for what? For the same motors with armature what reaction. As you can see, guys, here, this is without armature reaction. This is what? This is, sorry, here with armature reaction, and this is no armature reaction. And this is the what here? Ideal case. Okay. Now let's solve one example. Example 8.1. Okay, a very simple example. 50 horsepower, 2050 volt, 1200 revolution per minute DC shunt motor with compensating windings, has an armature resistance including the brushes, compensating windings, and interpoles of what, guys? 0.06 ohm. Its field circuit has a total resistance R adjustment plus R field of 50 ohm, which produce a no load speed of what? 1200 revolution per minute. There are what? 1200 revolution per minute per pole on the shunt field winding. So A, find the speed of this motor when the input current is 100. For B, when the input current 200. For C, when the input current is 300. And for all three cases, calculate what? Induced torque for every what? For every current. Very simple example. It is repeated here for procedure for A, B, and C. Okay. By the way, this is the equivalent circuit for this example, as you can see here. This is now can you see, this is VT 250, and we have IL goes to the armature and the shunt here. Okay, this is the both R adjustment RF 50 ohm, and as you can see now RA will be always with the low value. Okay, like 0.06 here in our example. So IL will divide what, guys, here? IL will divide to both here IA and what? Here IF. Okay, so IL will equal what here? Will equal IA plus what? Plus I plus IF. Okay, let us here now see the solution down. This is the solutions here. The internal generated voltage of a DC machine with its speed expressed in revolution per minute. E equal K multiply flux multiply the speed here. Okay, this is the equation. Since the field current in the machine is constant, because Vt and the field resistance are what? Both constant. And since there are no armature reaction effects, the flux in this motor is what? The flux will be constant because there will be no now armature reaction. The relationship between the speeds and internal generated voltage, okay, voltages of the motor at two different load conditions is thus. Okay, this is the equation. We will conclude now from this equation for the speed. Now the constant K cancels because as you can see here, okay, as you can see we have both K, we can cancel here K with K here. Okay, since it is a constant for any given machine, and the flux cancels also as described above. Also we can cancel what? The flux. Okay, because we are talking about the constant here. The flux will be constant. So we can calculate this equation here. Memorize this equation, guys. N2 will equal what? EA2 over EA1 multiply what? N1. Okay, this equation we will use it to find, okay, for at any value of what? Input current. Okay, Now at no load the armature current is 0. Okay, at no load armature current what is 0. So EA1 equal what? VT equal 250 volt, while the speed in 1, okay, we have already given from the question in 1200 revolution per minute. So for A now, if IL equal 100, then the armature current in the motor is, we can find IA. Yes, IA will be equal what now? I equal IL minus IF. Okay, because we have already IL will equal what? IA plus IF. Okay, so we need to find IA, sorry. So this IL will be minus IF. Okay. So IF will equal here what? VT over RF. Already we have giving IA load, so this is 100 ampere minus VT 250 over what? RF 50. So the answer will be what? 95 ampere. Therefore EA as this load will be what? Okay, we can write the equations here. EA equal VT, EA equal VT minus IA multiply RA. 250 volt minus what? IA already we calculated 95. RA from the question 0.06. So the answer will be what? 200. Okay, 44.3 volt. Now we can find the speed. The resulting speed of the motor N2 equal what? EA2 over EA1. EA2, this is the, we will calculate it, this one, EA2, okay, this value here, okay, over EA1 from the question, 250 multiply N1. N1 also from the question here, 1200. So the answer will be what? Okay, the answer will be 1170. Now for B, part B, just we will change the load current to what? To 200 ampere. You have to do the same things, guys, here. Find IA, calculate IA, it will be 195 ampere. Then calculate EA, armature voltage. Then it will be 238.3 volt. Then we have to find the speed, the new speed in 2. It will be, guys, here 1144 revolution per minute, as you can see. Okay, if the load current increase, the speed will goes down, decrease. Okay, also you have to do the same things for C here. I load will be now changed to be 300 ampere. Then we will find IA. Okay, IA will be 295 ampere. Then EA will be what, guys, here 232.3 volt. Okay, the new speed will be into will be now 1115 revolution per minute. Okay, let's come to the last what here part to find the induced torque. We have from the question here the induced torque in the we have B converted first here, B converted will equal EA multiply IA, and B will be power equal torque induced multiply what? Omega. Okay, so now we need to find the torque. So torque induced will equal EA multiply IA over what? Over the speed. Okay, therefore then the induced torque when I load equal 100 ampere. Okay, we will choose IA and what? EA for the same for the same value of what? Of part A when the load current is equal 100. Okay, this is EA and this is what? IA over the speed, over what? The speed. We have to change the speed, guys, here. This is the conversion here. Okay, just let's make zoom in here. Okay, can you see here? This is the speed we already calculated. Okay, 1173. We have to convert it. Okay, from revolution per minute to what? Rad. to rad per second. So we have to multiply by 1 minute over 60 seconds, 2 by, okay, multiply also 2 by, and this is what, guys, here, this is the equations, okay, this is the equations to convert between the speed from what, guys, from revolution per minute to rad per second. You have to multiply here 2 by over 60, multiply the speed, okay. This is here the conversion of the speed. So the answer will be what here? 190 Newton in minute, okay, in Newton in meter, okay, in m. Also here I load, for the I load when it will be 200 ampere, okay. You have to find the induced torque, just convert make conversion for the speed, okay, and this is the answer for the induced torque, and this is then also the answer for the last solution for the induced torque for part C. Okay, guys, so this is the end of the solution of example 8 what, guys, here 8 here 1, okay, example 1. Now we'll come to two parts here. Speed control of a shunt DC motor. There are 3 methods in use, which are number 1 here, number 1, changing what, guys, here, changing the field resistance. To understand what happens when the field resistors of DC motor change, assume that the field resistors increased. Okay, guys, only here you can just follow the steps, the procedures here. Increasing RF cause IF to decrease, decreasing IF, decreasing the flux, decreasing flux, lowering EA, decreasing EA, decreasing IA, decreasing IA, increasing torque induced, okay, then increasing torque induced makes torque induced greater than torque load, and the speed will increase, okay, EA increased, okay, will EA, the armature voltage will increase, then increasing A increases IA, decreasing IA, decreasing the torque induced until here torque induced equal torque load at higher speed, okay, omega. Okay, this is the first step here. The second one will be changing the armature voltage without changing the voltage applied of the field. Just here follow the steps here. The last procedure, guys, here in inserting a resistors in series with the armature watt circuit, okay. In this way we control the IA, and the effect is to drastically increase the slope of the motor's torque speed characteristics, making it operate more slowly if loaded. Since the losses in inserted resistors are very large, then this method is rarely used. Okay, this method is rarely used. Now last here, now the effect of an open field circuit. Previously it was mentioned that as the field resistance increased, okay, the motor speed increased too. But what happened if the field resistance really increased here, field resistance? Or in other words, what happened if the field circuit actually opened while the motor was running? From the previous discussion, the flux in the machine would drop drastically, okay, and then EA, okay, would drop with it. This would cause a really enormous increase in armature current, IA, okay, and the resulting induced torque would be quite a bit higher than the load torque on the motor. Therefore, the motor's speed starts to rise and just keeps going up. For this reason, it is prevented to use fuses or any other circuit breaker in the field circuit of the shunt DC motor. Moreover, it is used to add some protection devices that cut off the power supply if the field circuit opened. Okay, this is now DC motor problem in starting. Okay, in order for DC motor to function properly, it must be protected from physical damage during the starting period. At starting condition, the motor is not turning, and so EA will be what? EA will be 0. Since RA is of a normal DC motor is very low, as you can see, guys, RA will be what? Will be always very low. Then a very high current follows. IA will be what? High current at starting. The sudden increase of the current could run a risk. Could be, okay, there will be a risk, okay, to the here. Maybe burning out the armature, damaging the commutator and the brushes due to a heavy sparking, okay, because we have here high current IA. Overloading the feeder, snapping of the shaft due to the mechanical choke, damaging the driven equipment because of the sudden mechanical hammer. So what could be the solution for this high current here, guys? Okay, so the solution will be what? Is to what? Insert as starting what? Resistors in series with the armature to limit the current flow until EA can build up to the limiting. This resistors must not be in the circuit, okay, permanently, because it would result in excessive losses and would cause the motor's torque speed characteristics to drop. Okay, so the resistor will be only for starting, and this is here, guys. Reverse the direction of the rotation. This can happen by interchanging the terminals of either, okay, this is one armature coil, okay, or what, guys, here, a shunt field coil, okay, as we can see in the practical period session. Okay, we can change the armature coil or what, shunt field coil. Note that if we interchange that terminal for both coils or the terminals of the power supply, then the motor will rotate with the same direction. Okay, so we have two procedures here. Number one, interchange armature coil. Number two, or interchange the shunt field coil. Only one of them you have to follow. Okay. Figure 5. This is a shunt motor with what? Starting resistors. Okay, this is the guys here. Are starting only for starting. Okay, to what? To reduce, guys, what? To reduce the starting current, because we have a high starting current. Okay, so just we are using for what? For thing. Then we can what? Cancel this resistance after the motor running. Okay, start. Last problem, guys, here. Problem, very similar problem here. A 250 volt shunt motor runs at 1000 revolution per minute at no load and takes 8 ampere. Okay, the total armature shunt field resistance are here 0.2 ohm and what? 250 ohm. Calculate the speed when loaded and taking what? 50 ampere. Okay, assuming what? Assume the flux to be what? Constant. Okay, so formula used N, okay, over Ni, EA over EAI, okay. N, this is the speed, and EA, and this is the what shabab here, guys, armature what voltage, equal what flux I over flux over what flux. Since here the flux will be what, guys, from the question is assumed to be constant, so we can cancel the flux. So we'll have what here, N over Ni equal what, EA over what, EAI, okay. So we'll find first I shunt, okay, or I field will be what shabab here, VT over what, over R shunt. V terminal 250 over what, R shunt, how much here, this is here 250. The answer will be what here, 1 ampere. Then IA will equal what, guys, will equal 8 minus 1. 8 minus 1. What is 8 here, guys? Here 8. This is what? This is here load, IL. Okay. This is I what? L minus what? Minus I minus I what here? We already find it. I shunt. Okay. So 8 minus I shunt. The answer will be what? 7 ampere. Okay. IA equal what, guys? IA equal what? 50 ampere. 50 ampere minus what? 1 ampere, which is will be what here? 49 ampere. Okay, 49 ampere. Then we have to find EAI equal what? V minus I. Okay, IAI multiply RA, 250 minus 7 multiply what? 0.2. This is what? RA, guys. It will be what? 248.6 volt. Also again here the same equation, EA will be equal what here? 49. Just he will change the values here for the armature current and 49. Okay, it will be 240.2 volt. Now we can what? Find the speed now, guys. N over what? 1000 revolution per minute equal what? 240.2 volt over 248.6 volt. So just make a cross. The new speed will be what? Equal 966.1 revolution per minute. This is, guys, here the solution for this problem 4, and I will give you an assignment. Okay, try to solve this assignment. I will okay, it will be very simple for you, inshallah. Okay, through the blackboard. And thank you, and see you again.